All right, our last speaker of the session is George Porter. He is currently Assistant Professor of Computer Science at UC San Diego and Assistant Director of Center for Network Systems there. His research focuses on data-intensive computing with emphasis on data center networking. In particular, he wants to enable developers and operators to build systems that can process massive amounts of data.
Thank you so much, Jenny, and thanks, Andy. So first of all, it's a great honor to be able to come and give a talk at this event. It's really exciting to be here. So I'm Randy's 39th PhD, graduated in 2008, and I'm now at UC San Diego. And one of the things I wanted to do this morning was sort of talk a little bit about some of the work we've been doing over the last 5 years or so on improving resource efficiency in data processing systems, specifically focusing on IO-bound applications. So these are things like MapReduce, sampling, quartile estimations, large-scale sorting. And one of the things that we've been trying to do is address this huge gap between the delivered performance of applications and the raw computing power that actually underlies these applications. And this problem really kind of came to our attention. We were really introduced to it while working on networking. So when I joined UCSD, there was an active project underway to work on improving the way that networks are built. So traditionally, you'd look at a data center network like this where you've got various amounts of hierarchy, and at each layer of hierarchy, you end up with these bottlenecks. And so you may have 5-to-1 or 40-to-1 or even 200-to-1 networking bottlenecks that caused applications to be starved for bandwidth. And so there was this move to build scale-out designs that kind of got rid of those bottlenecks. And this is extremely good for building applications, especially as hosts get faster and faster. As we go from 1 gig to 10 gig hosts and now 40 gig hosts, we need to get rid of these bottlenecks to get efficiency. But one of the things that was kind of interesting was that it became very difficult for us to actually test this system because we had trouble pushing all this data through the network. So you can never actually get rid of a bottleneck. You can only move it from one place to another. Every system has bottlenecks in it. And so we successfully moved the bottleneck away from the network, and this exposed a lot of challenges in building the application. And this was a really exciting time to be there. So we said, you know, let's just build some super simple application. Let's forget about this sort of complicated data analytics processing. Let's just do sorting. Like, sorting's great. We all know how to do it. We learned it our freshman year. You know, it's a common benchmark. Jim Gray had created this annual sorting challenge, and it's just actually a lot of fun because you know when it's right. It's very rare that you have an application or an evaluation methodology where you know absolutely that, yes, this data is sorted or it's not. And it's very applicable. You know, it's built into data processing systems and databases and other things like that. So our plan was, you know, this is extremely easy, right? So we got an MRI from NSF to build this large-scale cluster. And we said, well, let's just get enough hard drives to drive 10 gigs, and we'll put that in each machine. We'll do about a week of coding, maybe a day or two of tuning, and now we'll have an application that will max out our 10 gig network. And then we can start looking at, you know, move on. Well, it turns out that that was a longer story. And so 5 years later, we're sort of finishing this project up. And so I just want to talk a little bit about some of the high points along the way. The reason these applications couldn't really keep up, it's really just about I/O. You know, it's about moving data to and from storage, moving data in between the nodes inside of these clusters. And the result of these bottlenecks is that, you know, if you've got these bottlenecks in your system, servers end up waiting for data, causing them to be idle, causing you to burn up a lot of energy, power, cost, and everything else. And so you end up provisioning clusters that are larger than you actually need in order to kind of meet whatever SLAs, whatever kind of requirements that you've got to build your system. And so one of the things we were trying to do is sort of recapture this I/O efficiency. So we really were kind of relentlessly focusing on the I/O subsystem between storage and between these different nodes. Now, as you've seen, this was not kind of going on in a vacuum. At the same time, so over this sort of 5-year period, there was this absolute renaissance in the way that people were building these systems. And people like Andy, people like Spark, Mesos, you know, I say go Bears because so much of what was happening in this data processing world was happening right on this campus. And so suddenly there were systems that actually wanted the efficiency because they were building such high performance data processing systems that the network became kind of a bottleneck in some sense. And so this was really great. Now, obviously, resource efficiency is important to, you know, all of these different projects. And in fact, there was a lot of effort in different papers, in different ways of kind of improving efficiency. And I want to say that we really kind of thought of the work that we were doing as quite orthogonal to this line of optimization because, you know, one way of kind of handling efficiency is to focus on sort of scheduling and bin packing, and there's a lot of really important sort of fundamental work going on in there. What we were really focusing on was sort of what goes on inside the things you're bin packing. So can we actually make a single task, a single process, very, very high, highly efficient from an I/O point of view? So just to give you a kind of quick overview of what I'm going to talk about. So we initially focused on sort of building a sorting and data processing system for dedicated hardware. I'm not really going to talk about that so much today, but I want to talk about the second aspect of this was taking that line of work, taking that software and focusing on the cloud. So we actually focused on deploying these pieces of software into shared cloud platforms because you get a bunch of resources that you wouldn't otherwise have. But it also exposes some unique challenges because it's not dedicated resource. It's a virtualized shared environment. And so we have two kind of examples of that from the last year or two that I want to speak to a little bit. Okay, cool. When I talk about data processing, commonly what we mean are things like MapReduce. Andy brought up some of the more interesting ways of specifying computations of these systems, but for this talk I'm going to talk about MapReduce, where you want to apply some processing operation to a data item, and then you want to do some sort of aggregation step. And you may have pipelined versions of this where you apply this in an iterative fashion. But what you find out is that you've got this kind of map task, you've got some kind of aggregation step, and in between is this enormous sort of all-to-all shuffle where you've got to get all the data between all of your operators spread across your cluster. And oftentimes, this all-to-all shuffle and sorting operation becomes an enormous challenge. It's very difficult to do that. Parallelizing individual computation is relatively straightforward. It's when you start doing that aggregation step that it becomes really challenging. Now, we were not the first people to identify this as an enormous challenge. In fact, Jim Gray, the late Jim Gray, wanted to draw people's attention to the importance of I/O when you're building data processing. And so one of the things that he did was to help create this annual contest. And it was a sorting contest. And what was nice about the sorting contest was that it moved people's attention a little bit away from things like MIPS and CPU-focused benchmarks to the sort of end-to-end system performance that includes I/O and storage. When that benchmark was created, this was 1985 or so, big data meant 100 megabytes. Like that was sort of big data processing. Over the years, that shifted. By 1999, it was sort of a terabyte. And so the winner of the terabyte sort was the Now project here at Berkeley. I had an opportunity to go visit the Now cluster last night, which was very exciting for me. And then by sort of 10 years later was these large-scale open source distributed software tools like you just heard about. And so Hadoop was the record winner in 2009. So this was kind of the context. This was the environment that we walked into when we kind of began this project. Now, at that particular time, people were really focused on sort of building something that was scalable. And so there was actually a pretty big gap between the measured performance and the potential performance. And so if you look at some of those GraySort results, what you would see is that there was an enormous amount of inefficiency. There was a lot of I/O and CPU that was sort of left idle. And so when we started, there was this 100 terabyte winner had used about 3,500 nodes to sort 100 terabytes in about 3 hours, which represents about 1% overall system efficiency. And now, it could scale to 3,500 nodes, which is actually a pretty amazing feat. And so I don't want to complain, but this was kind of what we were targeting at. And we said, well, if we can do this in 3 hours at 1% disk efficiency, we sort of said, well, if it takes this amount of nodes to do something at 1% efficiency, could it be possible to actually do the same amount of work in the same amount of time using 35 nodes or whatever else? And so that was kind of the hypothesis of the project when we started. So the kind of key insight we had was that we wanted to get rid of as many IOs as possible. And so if you're sorting data, it requires at least 2 reads and writes per record in the worst case. And so we said this 2 IO property basically means that any system that you build, if it kind of meets this, then it has this 2 IO property. And so we ended up designing this distributed sort application that has this 2-pass design, which means that it only touches data exactly twice in the worst case. So we were able to ensure that we didn't end up issuing any additional IOs that we didn't have to. So that was one source of efficiency. And then we just worked on making the software as fast as we could. Now, the real challenge to doing something that meets this IO limit is the fact that you've got imbalance. If we had perfectly uniform, homogeneous data on a perfectly homogeneous cluster, this would be a really easy problem. But in reality, data is extremely messy. it's you've got nonlinear effects and a lot of variation in the way that data looks like. And so we have to be able to handle a lot of this imbalance. And so all of this imbalance tends to cause additional IOs that are not strictly necessary, which kind of lowers overall performance. Failures are also kind of fall into this case as well. And so we sort of focus on balanced computing in this distributed data processing system. And this was especially difficult in the cloud because not only are we dealing with non-uniformity in the data and non-uniformity in the compute, but we're also dealing with non-uniformity in the platform itself between the virtual machines and the network as well. So we designed this system. I don't really want to talk too much about it, but we ended up deploying it in a controlled environment initially. So this was this cluster that we kind of built up. And the one thing I want to say is these are these different sort records. We were able to kind of to beat this Hadoop record. And the hypothesis is that we could do this in about 35 nodes. And we got at least into the right order of magnitude, which as far as a computer scientist is concerned is equal. So as long as it's in the same order of magnitude. And then like any record, by 2013, we sort of got taken over again. And they, Hadoop was able to push beyond a terabyte a minute. And one of the things I want to say is that this was a little bit bittersweet because one of the reasons that this contest measures performance in terms of terabytes a minute is that Jim Gray said, well, if we measure it in terabytes a minute, what that means is that when we hit 1.0 terabyte a minute, we know we're done. Like we've basically solved this problem. So they were able to get 1.4 terabytes a minute. But I want to say that it wasn't all bad news because at the same time there was this new GraySort contest that got designed, which was focusing really on IO efficiency. And that was actually what our interest was. It was not so much absolute performance, although that's good. It was really about how resource efficient can we get. And so the key thing was that we were able to push a lot of resource efficiency. So I'm running a little bit low on time, so I want to move on to talking a little bit about what it takes to actually move things to the cloud itself. So when you deploy some system to the cloud, you have an enormous choice on actually what your platform is going to look like. How much compute, how much memory, what kind of storage? Do we use local storage, SSDs? Do we use network-based storage? What kind of network are we going to deal with? What kind of network properties do we get from our cloud provider? And by the way, EC2 has 53 VM types. I only checked that last night. It's probably 54 or 5 now. And so our approach was basically an observe, analyze, act approach, which I stole directly from Randy, the observe, analyze, act approach, which was basically to measure in microbenchmark storage and networking in our cloud provider over time. Use that to build an application performance model. This model allows us to predict a particular cluster configuration, both in terms of time and money, at small scale. And then what we did was we deployed that same sort of recipe at large scale, and then we were able to compare the predicted performance to the actual performance. And this was how we could measure sort of how well this model was holding up. Now, this is not actually that easy to do. This is an example of a couple of the VM types you can get. It has the cost, the predicted cost of sorting 100 terabytes in the first column. But then it gives you the cost of each individual virtual machine in the second column. And one of the things you can see here is that there is 2 orders of magnitude difference in terms of the cost to run a particular job, depending on what VM type you pick. And so that's a huge amount of difference. But the second thing is that 2 jobs that are only about 50% apart in terms of the cost of running the job are really an order of magnitude apart in terms of the cost of each underlying VM. And so there is this incredibly nonlinear relationship between the building blocks you can build upon and the total performance of the system as a whole. There's also issues about capacity. So for example, in order to run a sort of 100 terabytes on M3.medium, you would need 75,000 VMs, which you're not likely going to be able to get. And so we had to kind of rule out some of these cases that required a ton of virtual machines. So the takeaways here are that we had this huge potential in terms of gains that we could get if we picked the right cluster. There was this nonlinear effect, and the storage capacity is kind of a big issue. So what we did was we sort of modeled the storage. We also modeled our network effect, and I'm going to reorder this in terms of increasing cost on the y-axis across a bunch of different virtual machine configurations. But the real thing that I just want to point out here is that, for example, I'm highlighting this HS1.8x. This is a storage-optimized VM type. So this you would think would be really good for doing distributed sorting. And it is actually pretty good if you just look at its storage performance. But when you actually factor in the fact that you've got this shared network, and that network is becoming a bottleneck in this cloud environment, it ends up actually not being a very good choice to pick. And so this kind of gives you some sense of what you have to do. And so we sort of ended up kind of looking at this and trying to pick a cluster that would give us the best bang for the buck given all of these different constraints. So that we found that, in our case, the network is actually the bottleneck. And so there's all, with Jim Gray's sort competition, there's all these different categories. And so we deployed this on Amazon on 178 VMs, which was simply the most we could get from them. We would have wanted more, but that's all they had, I guess. And we were able to get the 6.76 terabytes per minute result, which was almost 5 times faster than the previous winner. And that was good. It turns out we ended up not winning that year because we lost to BaiduSort. So Baidu is this Chinese search company. And so we were like, oh, man, they got 8.38 terabytes a minute. Like, that's really great. And so we started looking through their submission, and we were super bummed. But then what was great was we realized they actually just implemented our system from the paper. So, and they actually used 5 times as many nodes as we did. So we were like, OK, well, it's not too bad, I guess. And so, you don't just care about raw sorting performance. Sometimes you care about making sure that the system is fault tolerant. And so there's another aspect of this competition that has to do with fault tolerant computing. And we were able to deploy that into Amazon. And we actually tied with Apache Spark run by Databricks. And so what was kind of interesting about this was that we actually picked the same exact cluster configuration type. So we said, OK, well, we're not doing anything super crazy if these super smart people ended up picking the same type of a cluster that we did. And what was interesting, too, is there's now, as part of this, a contest that's specifically focused on cloud cost in this CloudSort record. And it turns out that when you deploy to the cloud and you worry about persistent storage, this changes your balance point somewhat. And so we ended up setting this contest result where we were able to sort 100 terabytes for $451 in the cloud. So we're like, OK, that's pretty cool. And we had, in that case, 330 nodes on Amazon. Now, we didn't want to kind of restrict ourselves just to Amazon, but so we looked at other providers as well, and so we looked at Google. And one of the major research questions we had was sort of, how do different providers compare in terms of I/O efficiency, like what primitives they offer, what properties they give you from their network. And so we deployed our code to Google Compute Engine. We ended up recalibrating our prediction engine based on the observed behavior of that environment. And I don't want to get into tons of details, but we basically picked some particular VM configuration that they've got. One of the things that was interesting was that actually, unlike Amazon, there is no local storage in Google. They just don't even give you that as an option. So we had to kind of recalibrate our model a little bit. And there was a bunch of details that we dealt with that I can talk to you about offline if you want. But one of the things that was really cool is that even though we didn't have local storage, we were able to decrease the cost of that sort by a factor of 3. So if you look at this record that we got, we had a $451 sort. With TritonSort, we were able to do that in Google for about $150. And so we were really happy that these techniques kind of generalized to other platforms as well. All right, whew, a little bit of a whirlwind there. So before I kind of wrap up, I want to just say that one of the things that's great about doing academic research is that a huge impact that you get from your project is not necessarily software and it's not necessarily papers, but it's people. And so one of the things that has been really great about this project is we've had a lot of project alumni who have gone off and are busy making great contributions in the wider world. Alex Rasmussen is off to Trifacta, so he left to go to Trifacta. Harsher is a professor at Michigan. Mike Conley just accepted a position at Google maybe 3 weeks ago. Radhika is also at Google. Alex Pucher, who was on the original TritonSort papers, now at UC Santa Barbara as a PhD student. And we even were able to find a job for one of our colleagues, Amin Badat, who's now at Google. So in conclusion, I just want to say, we've really been focusing on efficiency at scale. And I want to say that that involves sort of bin packing and scheduling, which is very much the comfort zone of venues like SOSP and SIGCOMM. It's also important to look at the systems aspects as well, sort of down at the low level. How do you actually get efficiency even within a perfectly scheduled system? Shared cloud platforms can be efficient in terms of cost, in terms of absolute performance, in terms of time. There's no fear for running on these shared cloud platforms because you can actually get performance out of them if you engineer your system correctly. And we're sort of wrapping up the sorting aspect, and we're actually looking now at staged, pipelined computing over video content. And so I'd love to chat with you maybe at the breaks or something like that if you're interested in that. All of our code is online at GitHub if you're interested in downloading it or running it. There's some scripts that allow you to deploy sorts to Amazon. And hopefully we'll be able to get our code to Google relatively soon. And with that, I'll wrap up and ask for some questions. Thanks.
The mic. So thanks for a wonderful talk. My question was, when you went into the cloud benchmarks, you have you talk about per dollar in the metric. What I don't understand is why the sort benchmark in the traditional setting doesn't say, it's 100 terabytes, or maybe next year it's 200 terabytes or whatever. But why don't they have a dollar thing? Because it struck me as weird that somebody with 100 times as much cost is considered a better solution.
So I think there was two parts to your question. One is that the benchmark is getting bigger over time. So next year it's going to be a petabyte. So you can't sort 100 terabytes.
Yeah, I guess the question is, why isn't the traditional sort, maybe I misunderstood, but why doesn't it have a terabyte per second per dollar as the
cost? Cost. Yeah. Well, there's a bunch of different strains. There's how many records you can sort per joule, so that's an energy basis. There's one which is just absolute cost. One's absolute performance. There is not yet one that intermixes those two. So if it takes 5 years to sort the data, but it's cheaper somehow, you would actually win on this cost basis, even though the absolute performance is significantly worse. So it's an evolving benchmark that includes all of these different metrics, and at the moment.
Sorry, but what's the difference? Why is it on the cloud the right metric is terabyte per second per dollar, but not traditionally?
Oh, no, so the winner of the traditional absolute time is done on the cloud as well. Unless I'm misunderstanding your question.
No, it sounded like for the traditional thing, you were comparing terabytes per minute.
Yeah,
when you went to the cloud, you said the right metric is terabyte per minute per dollar. Why is that? What's the difference? Why is there no dollar in one of them and a dollar in the other?
Oh, so there's no dollar in the traditional one, I think, only because it's just a raw performance situation. Like how much, it doesn't matter how much you spend. Spend as much as you want. But it turns out that you can't always buy performance with money. It's hard to do that. So, like, you can spend a lot on a cluster and still end up with a lower performance per dollar.
It's also difficult to actually, just to help you with an answer.
Yeah, I'm not sure I understand.
But, to you, that's exactly right. It's just like quals. So.
You never stop becoming someone's advisor. It's a tenured position, but go ahead.
It's just that in the cloud, you actually quantify the cost. How much does it cost to lease this instance for an hour to do a particular job? Whereas you have a cluster in the basement at UC San Diego, how do you, it's been sitting there for 5 years, how do you amortize it and so on? It's very difficult to actually assign a cost to the non-cloud because the cloud has the price so obviously associated with it.
Thank you. Thank you, Randy.
Great answer, George. Way to go.
Thank you. Thank you. Yeah, I picked my advisor well. So.
Have you asked? He doesn't believe me, though.
No, because he said it, I'm okay with it. I would have argued if you had to answer that way.
Any other questions? Just curious, have you looked at power? I mean, in terms of...
So we did look at power. We hold the record for the most efficient in terms of energy efficiency. We can't do that with the cloud, though, because, and we actually talked to Amazon, and they had a huge email exchange internal to their company about, can we figure out how much power your virtual machines are using? And the answer was that for various reasons, we couldn't get that data. So we weren't able to figure out the actual energy efficiency of the cloud. So, yeah.
Cool. Thank you.
Thanks, everyone.